Generalized Second Law and the Unity of Physics. Ms. Welcome.
Thank you. So it's a great pleasure to be here and to be able to talk. So I thank the organizers for this wonderful meeting. In view of the subject of my talk, I thought it would be appropriate for us to remember Jacob Bekenstein, especially during it. I was very saddened, as we all were, to hear of his sudden recent death. So that's why I've dedicated this talk to his memory. So I'm not going to talk about any work that I have done, so all of this will be about other people's work, but there's a particular question or problem that I would like to work on, and I'd like to hear your thoughts on that problem. I'm going to set out a point of view or a program or maybe an attitude, a collection of thoughts or ideas about black holes, black hole physics, and in particular black hole entropy and black hole thermodynamics, which I've developed by being influenced by many people over the years, starting with my first teacher on these matters, Malcolm Perry, who's here, and of course by Stephen, and then in more recent times by Jacob Bekenstein, by Ted Jacobson, by Aaron Wall, who's a postdoc at Princeton, and most particularly by Raphael Sorkin. And I'll show you along the way what particular aspects are due to these people. So you don't, in this audience, I feel a little embarrassed at presenting this slide, but nevertheless, it's so wonderful that I don't apologize. So 1973, Bardeen, Carter, and Hawking published their paper, The Laws of Black Hole Mechanics, in which they exhibited this remarkable analogy between the classical laws of black holes and the laws of thermodynamics. And of course it rhymes nicely, so that I'm sure that was deliberate choice of title to get that rhyming nice. And here is the analogy, a summary of the analogy, where kappa is the surface gravity of the horizon of a stationary black hole, and A is the surface area of the horizon. Surface area in general, it doesn't have to be a stationary black hole. And here are the laws. So on this side are the laws of thermodynamics. On here, this side are the laws of black hole mechanics. And there are 4 laws. So the 0th law of thermodynamics is that the temperature is constant throughout a system in thermal equilibrium. On the black hole side, the result is that the surface gravity is constant on the horizon of a stationary black hole. The first law of thermodynamics is what we now understand to be the law of conservation of energy. And on the black hole side, we have this rather mysterious law, well, what looks mysterious. And the analogy here is more than analogy, meaning it's a physical equivalence in 2 respects. So one respect, of course, is that we know that mass is equivalent to energy, so the mass of the black hole here, it really is the energy of the black hole. The work terms that appear in the first law of black hole mechanics really are work. They're mechanical work that the black hole does, similarly to the mechanical work that the thermal system does. But then there's this mysterious thing here. Here we have TDS, temperature times change in entropy, and here we have this mysterious thing, the surface gravity times the change in the area up to this factor of 1 over 8 pi g. So there's an analogy, obviously, structural analogy between these 2 things, but it's physical in the sense that E is really physically M, and these are really work terms, but then there's this strange thing here. And the second law of thermodynamics is that the entropy of an isolated system can't decrease. And on the black hole side, we have Hawking's area theorem, which is that the area of the event horizon of a black hole cannot decrease. And then the third law, which I'm not sure, I've never really understood what the third law is or its status, but you could perhaps you could state it as that the temperature of a thermal system can't be reduced to zero in a finite process, and the black hole side is that the surface gravity can't be reduced to zero in a finite process. So this is really a remarkable analogy, and should send shivers down your spine. But the analogy wasn't complete. The strange formal analogy between TdS and kappa dA just stood there as this analogy, and it took more than that to make these two, the analogy a truly physical correspondence or physical equivalence. And of course, we know what that more is now, and that more was Stephen Hawking's discovery of black hole radiation, that black holes really do have a temperature, they are thermal systems, and that breathed life into the analogy. It made it really a physical equivalence between these two sets of laws, and it put finally on the firmest of foundations Jacob Bekenstein's suggestion that black holes have entropy. So without the black holes having temperature, the conjecture that a black hole has an entropy proportional to the horizon area couldn't fly. But once Stephen had discovered that black holes really did have a physical temperature and radiated like hot bodies, then the notion that the black hole actually has a physical entropy proportional to its horizon area made total sense and fitted into the picture completely. So now we have the laws of black hole thermodynamics, which unify together general relativity, quantum field theory, and thermodynamics in this astonishing and astonishingly beautiful way. These are really the same laws, so that there's no difference. The laws of thermodynamics and the laws that govern black holes, so long as we take quantum effects into account, they're really the same physics. So the zeroth law is that the temperature is constant on the horizon of a stationary black hole. So you can think of the horizon as being a system in equilibrium. The first law is the law of conservation of energy. And instead of the second law, we now have something which Bekenstein called the generalized second law, which is that the total entropy of a system cannot decrease, of an isolated system cannot decrease, where by total entropy we now understand it to be the sum of the entropy of the matter outside any black holes plus the entropy of the black holes themselves given by the surface area of their horizons in Planck units. And I claim that this is the greatest unity yet achieved in physics. Herard is no longer here, so I'm not sure in this audience I would get much grief for making this claim. Maybe some particle physicists would claim that the Standard Model has a better claim than this, but I'm going to run my flag up the flagpole and say that to me this is the greatest unity yet achieved in physics, because it brings together these completely seemingly diverse areas of physics. So what should the Einstein equations know about thermodynamics? Emil?
Experimentally.
Okay. Fine, I'll give you that.
Since Gerardo is not here.
Thank you, yes.
Sorry.
I do agree. Nevertheless, it's only partial, this unity. To perfect it, we need at least two more things. We need to understand the statistical mechanics of black hole entropy. We know numerically what the value of the black hole entropy is. The number, we know what its value is. The value is its area in Planck units, up to a factor of order 1. but we don't know what the microstates are to which that entropy corresponds. What are the microstates which are counted by this black hole entropy? And we don't have a proof of the generalized second law. So this generalized second law is a proposal, a conjecture, and we don't have a proof. We have some thought experiments, and what I'm going to show you in this talk are a proposed proof of the generalized second law in a semi-classical setting, which would be completely general for any kind of state of matter outside the black hole. Okay. So just one more thing before I go on to talk about the generalized second law. There's a further inspiring glimpse of unity, which is that black holes are just one example of other horizons, of a more general class of horizons called causal horizons. And it's been suggested that all causal horizons obey the laws of thermodynamics, where a causal horizon is the boundary of the causal past of a future infinite time-like trajectory. So black hole horizons, de Sitter horizons, and Rindler horizons are all examples of causal horizons. Every causal horizon looks locally like a Rindler horizon, and the thermodynamics of horizons, the idea is, springs from the structure of the quantum states of field theories in Minkowski space and their non-local entangled structure. So we heard from Klaus about their structure as two-mode squeezed states. And moreover, the fact that the usual Minkowski vacuum is a thermal state for the Hamiltonian that generates boosts. And there's much work on this understanding of where the thermalness of radiation from causal horizon springs. So we should, according to Jacobson and Parentani, we should think fundamentally about horizon entropy and not just merely black hole entropy. Black hole entropy is the best known example, but we should think more generally about horizon entropy, and that there should be a greater unity of our understanding which brings together all these different sorts of causal horizons. So we can bear that in mind, but I'm going to talk about only black hole horizons for the rest of the talk.
Hey, there's many interests out of talking about the others and others.
Oh, good. Oh, thank you. So, in fact, Paul already quoted to you this statement by Arthur Eddington, but it's so enjoyable that I want to quote it to you again. In fact, the quotation comes from a series of public lectures that he gave. They're called the Gifford Lectures. You can read them online. They're extraordinarily entertaining. Eddington must have been quite a remarkable person. But yeah, not just this quotation, but the whole lot is a really fun read, so I recommend them. So he says, famously, the law that the entropy always increases, the second law of thermodynamics, holds the supreme position amongst the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it's found to be contradicted by observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. Perhaps this is an exaggeration, but probably I'd hazard a guess that the exhibition of some perpetual motion machine in your theory or in your model would certainly be a severe disincentive to continue working on it. More persuasive than this hyperbolic statement is perhaps the subtlety by which attempts at counterexamples to the generalized second law fail. And the box-lowering example of Bekenstein, as analyzed by Unruh and Wald, is a case in point. So if you remember, that example is to take a box of entropy and to lower it towards the horizon so that all the energy of the box is extracted as work at infinity. So that as the box reaches the horizon, it then has zero energy as measured at infinity. So that eventually lowering across the horizon will not change the mass of the black hole at all, or by an arbitrarily small amount. But it will reduce the entropy outside the black hole. So it won't increase, doing that won't increase the horizon area, because it doesn't increase the mass, but it will reduce the entropy outside the black hole. So that would be a violation of the generalized second law. However, Unruh and Wald show that if you actually do this procedure of lowering the box towards the horizon, at each moment you can approximate the situation by having the box be static. And a static box outside the horizon experiences Unruh radiation. So there's a radiation pressure, and that pressure is larger on the front of the box than the back of the box, and so the box will reach a buoyancy point where, in order to get the box further towards the horizon, you actually have to push it, and then you have to do work on the box. You give it energy, and that energy is enough to be able to save the generalized second law. So that's a beautiful, subtle interplay between the structure of the vacuum in Minkowski space and the second law. So one can turn around these arguments and say that the second law can be a guide in physics, so in quantum gravity in particular. So it isn't enough to identify potential microstates giving rise to the area relation to black holes, and that's what most approaches to black hole entropy in quantum gravity have focused on. The generalized second law also needs to be proved, and this has been emphasized for a long, long time by Raphael Sorkin. So you can find area relations for microstate counting till you're blue in the face, but it doesn't show that you've discovered the physical entropy until you can show that the generalized second law holds. Or at least it's not an entropy worth its name. And turning this around, we can use the generalized second law to guide us towards finding those microstates. So the two things go hand in hand, they're bound together. Finding the microstates and proving the generalized second law go together. And Sorkin has proposed two proofs of the generalized second law. One is a sketch of a proof that would hold in full quantum gravity, and the second is a more fully worked out proof in a semi-classical approximation. Both of these proofs rely on certain powerful results about entropy and relative entropy, which I'm going to tell you now. So here's a definition of relative entropy. The relative entropy between two quantum states, rho and sigma, is this. It's the trace of rho log rho minus rho log sigma. And you can prove that this relative entropy it's not symmetrical between rho and sigma, you can see, and you can prove that it's always positive. And here's a theorem. If rho and t evolve in time, and they both evolve according to a completely positive linear trace-preserving map, then this quantity here, this relative entropy between rho and t, is non-increasing. And this particular version of the theorem was proved by Lindblad, and there's a whole set of such theorems for more and more powerful theorems using fewer and fewer assumptions. So, for example, Lindblad's original theorem assumes that these are density operators in a finite dimensional Hilbert space. And you can relax this condition of completely positive map to being just something called 2 positive, and you can extend it to infinite dimensional Hilbert spaces. And in particular, a very powerful version of the theorem is due to Ullmann, which doesn't use density matrices or Hilbert spaces at all, but is just, it pertains to states defined on star algebras of observables, which is probably more relevant to the case of quantum field theory in curved spacetime, where we know that that there are no Hilbert spaces, that you can't represent states on local algebras of observables on Hilbert spaces. So here's the theorem by Ullmann. So if rho and sigma are states, meaning these are linear operators on the algebra of observables, and if rho t and sigma t are their restrictions to some subalgebra, so AT is a subalgebra of A, then this relative entropy is again is non-increasing. So the relative entropy between rho and T, as considered as state on this subalgebra, is less than or equal to the relative entropy on the larger algebra. Okay, so in fact, I'm just going to use this version of the theorem, but we should bear in mind that there are more powerful versions with fewer assumptions. The other key aspect of the Sorkin proposal for proofs of the generalized second law is that there must exist an equilibrium state, in other words, a state which is preserved under this evolution, under this completely positive trace-preserving map. So here's the relative entropy again, and you can see that if sigma is preserved by the evolution, then this quantity, this relative entropy, is something which only depends on rho, and it's non-decreasing with time. So Sorkin's, and now I'm just going to tell you what the semi-classical generalized second law is. I won't tell you what the proof scheme is for the full quantum gravity version. This is just the semi-classical one. So it proceeds in the following way. We assume that we have a quasi-stationary situation. That's one in which at any time we can approximate the metric by an exactly stationary metric. And in this case, I'm just going to say, assume that metric is Schwarzschild. So it's non-rotating and uncharged. And the matter is quantum, however. So we can consider the matter to be gravitons or other quantum fields in the space-time. And here's the horizon. And we choose surfaces of constant t, where t is a coordinate which is compatible with the Killing vector expressing stationarity. So d by dt is, the Killing vector is d by dt. So for example, for Schwarzschild, there are these, people call them nice slices of constant t which pass through the horizon and foliate the whole of the space-time inside and outside the horizon. And let's assume that the state of the external matter is given by this density operator rho of t on the slice sigma of t. Now what we want, the generalized second law in this situation, is that on this slice, this later slice, the generalized entropy, which is the entropy of the black hole, the entropy of the horizon, which is 2 pi A2, where A2 is just the area of the intersection of this sigma 2 with the horizon, plus the von Neumann entropy of rho, which is minus trace rho log rho. That has to be greater than or equal to the generalized entropy on the earlier slice. So that's 2 pi A1, that's the entropy of the horizon here on sigma 1, plus the von Neumann entropy minus trace rho log rho of the external matter on sigma 1. So that's what we want. This would be a statement of the generalized second law. And we're going to use the theorem about this non-increasing quantity to prove that.
Could I ask a quick question? There's no coarse graining so far.
That's right. There's no coarse graining, yes. The only coarse graining, if you like, is that rho of t is a state on sigma only outside the black hole horizon. So if you like, you can think of rho of t as being the state of the matter on the whole slice, the whole Cauchy surface, sigma, which extends inside the horizon all the way to r equals 0, and then you trace out the degrees of freedom of the matter inside the horizon. So this is not a pure state. Yes. But exactly. Yes, that's right. But other than that, there's no coarse graining. So in order to define this non-increasing quantity, we need a state which is preserved by the evolution. But there is such a state in a Schwarzschild space-time, and that's the Hartle-Hawking state. So the Hartle-Hawking state is an equilibrium state. It's preserved by the evolution outside the horizon. And moreover, the evolution of rho of t is a completely positive map. It's an autonomous evolution because of the causal nature of the horizon. Given rho on sigma t1, we can work out rho on sigma t2 because the surface sigma t2 is in the future domain of dependence of sigma t1. So there is an autonomous evolution given by a completely positive trace-preserving map, which evolves rho from sigma t1 to sigma t2. So the conditions of the theorem hold. We have a rho of t which evolves autonomously. We have an equilibrium state, the Hartle-Hawking state, and here it is. It's e to the minus beta h, where h is the Hamiltonian, divided by the trace of e to the minus beta h. And the theorem thus gives us a non-decreasing function of rho. So now I've put a minus sign here. So the theorem said that the relative entropy was non-increasing. So with a minus sign, this is non-decreasing. And it's the relative entropy between rho and the Hartle-Hawking state. And that's given by minus trace rho log rho minus beta trace rho h minus beta log z. So we just plug in rho Hartle-Hawking into the formula for the relative entropy. And we get the following thing. So this minus trace rho log rho, that is the entropy of the state, the external state. Minus beta and trace rho h, that's the expectation value of the energy, external energy, minus beta log z. And here one should note that both this quantity and this quantity are formally divergent. They're infinite. The external energy, the external entropy is divergent because of the entanglement between modes on either side of the horizon of arbitrarily high frequency. So without any kind of high frequency cutoff, this entropy, this entanglement entropy of the matter outside the horizon is formally divergent. This is also divergent. One could ask the question whether the infinity here and the infinity here cancel out to give you something finite. I don't know whether that's the case. But we're actually only interested in changes of entropy here. So in fact, the fact that this is formally infinite won't matter when we consider just changes in the entropy. So let's consider changes in this quantity. And by conservation of energy, the change in the expectation value of the external energy has to be compensated for by a change in the mass. So delta E external is equal to minus delta, minus the change in the mass of the black hole. And by the first law, that is equal to minus TdS black hole. So here we're not asking about the origin of the black hole entropy. We're just assuming that the black hole obeys the first law. So we're not asking whether what the microstates are or anything. We just assume that the black hole obeys the first law. And when we therefore plug this into the change in the entropy, we find that the change in S external, which is minus trace row log rho, plus S black hole is greater than or equal to 0, which is the generalized second law. Okay, so there's a lacuna. There's a problem with this proof, and I don't know if any of you have seen it, but it was spotted and explained by Aaron Wall, and this is the problem. So this is the Hartle-Hawking state. This Hamiltonian is not the Hamiltonian on surfaces like sigma, which do not pass through the bifurcation 2-sphere. So this H is not the Hamiltonian H external, which is the energy on these slices, but I assumed that it was in the proof. I assumed that the expectation value of H was equal to the expectation value of the energy on these slices. So this H here doesn't generate, it doesn't generate time translations from here to here. It generates boosts. So if this is the horizon, this is the bifurcation 2-sphere. The H in the Hartle-Hawking state generates transformations between surfaces that pass through, hypersurfaces that pass through the bifurcation surface. So Aaron pointed this out, and he's produced an alternative proof which uses, I have to confess I don't understand very well, but it uses an algebra of observables defined on the horizon, and it's considerably more complicated than this 3-line proof that was given by Sorkin. So here's the question that I'd like to investigate and ask you: can this conceptually elegant proof of Sorkin be completed? Can we get around this fact that the Hartle-Hawking state is thermal on these slices, but apparently we don't know whether it's thermal on these slices. So one question is the Hartle-Hawking state thermal on these nice slices? And if it's not, is there some more subtle resolution involving some boundary term at the horizon or something like that? So that's the question, the open question, which I'd like to think about. There are other questions which are raised by this proof. So what about charged and rotating black holes? The obvious thing to try and do would be to try and replace this H here by H minus omega J minus phi Q. But this state can't exist. So there is no Hartle-Hawking state for rotating black holes. So this state, in some sense, must be a highly singular thing. It must have infinite expectation values, infinite matrix elements. There must be something very singular about about the exponential of this operator. So how can we overcome that and extend this generalized second law to charged and rotating black holes? Okay. So that's the open question. And then I'd like to end by showing you that the generalized second law is being used to rule things out. So Aaron has written 2 papers in which he's used the generalized second law as a guide to what is possible and what's not possible in let's say, semi-classical gravity, and perhaps extended to full quantum gravity. So I think we've heard many talks at this meeting about the concept of black holes which are non-singular, in which there's no singularity. Either the black hole sort of stalls at some finite finite density and doesn't reach a singularity, or it bounces and re-expands. And the way that those models are argued for, that they should be allowed despite the singularity theorems of Roger Penrose, is that, well, we all know that the singularity theorems assume energy conditions, and quantum fields can violate such energy conditions. So we can have negative energy, we can have violations of the null energy condition, which will allow us to evade the singularity theorems. So Aaron's idea was to use the generalized second law as a substitute for the energy theorems. Sorry, for the energy conditions. And he introduced the concept of a quantum trapped surface, something that was more general than just a classical trapped surface. And the notion of a quantum trapped surface is a surface on which the generalized entropy is decreasing on future outgoing null normals. So you can see how that's a generalization of the usual definition of trapped surface. So on the usual trapped surface is one in which the expansion is decreasing, or expansion is negative, sorry, on a future outgoing null normal, on all future outgoing null normals. So instead of the expansion, Aaron's replaced this by the notion of the generalized entropy. And he uses this to prove that the usual energy condition in the Penrose-Hawking singularity theorems can be replaced by an assumption of the generalized second law. So roughly speaking, if the generalized second law holds and the space-time is globally hyperbolic and a quantum trapped surface exists, then the space-time is singular. So you can't evade the singularity theorems if you want the generalized second law to hold. So the assumption of the generalized second law rules out bouncing universes, cosmological bouncing universes, non-singular black holes, traversable wormholes, and viable baby universes which branch off from mother universes. And all of it rules out these models in which the metric is everywhere Lorentzian and non-singular. So it says you can't have such models and still have the generalized second law hold. Secondly, in a second paper, he shows that in a 1 + 1 dimensional model, the generalized second law is violated for any horizon other than the causal horizon. So the causal horizon, remember, is defined globally. It's the boundary of the causal path of this infinite, future infinite time-like trajectory. And for that reason, many people feel uncomfortable with the causal horizon, the event horizon. It's what people call teleological. It depends on everything that happens in the future. So the position of roughly speaking, the position of the horizon here and now depends on whether or not some matter falls into it in the future. And because of that, it's very global. It's been criticized as being non-local. So Aaron shows that if you take the dynamical or trapping horizon, then the generalized second law is violated. And he explicitly shows that the validity of the generalized second law actually rests on this teleological nature of the causal horizon. Without that, the generalized second law will fail. And I should mention here, these generalized second laws, the generalized second law is quantum. So you can prove the classical law of area increase for dynamical and trapped horizons. It's only when you consider quantum matter that you see that the generalized second law is violated for these dynamical or trapping horizons. And then finally, Bianchi, De Lorenzo, and Smirlak look at more concrete, so these are theorems that Aaron has proved, but Bianchi, De Lorenzo, and Smirlak look more concretely at entanglement entropy production during gravitational collapse and evaporation in a concrete model of non-singular black holes with no event horizon. And they find a not very surprising violation of the generalized second law in the purifying phase. Of course, so the generalized entropy increases during the collapse phase, but because you know you've got to end up with a pure state in the end, of course, the entropy has to go back to zero again in the end. So the generalized entropy will decrease in the purifying phase. So there's a violation of the generalized second law. And Francesca's and Carlo's Planck star model couldn't be treated by these authors so concretely because that's the metric, the unknown quantum part of the metric isn't known, so that they couldn't do the same kind of exact calculation that they did in this concrete model. But if the metric there is non-singular, then it falls into the purview of Wall's theorem, and that would mean that it will also violate the generalized second law when there's quantum matter. Okay, so I'll summarize. So proving the generalized second law is a crucial part of understanding black hole entropy. It's not enough just to demonstrate that in your favorite model of quantum gravity, you can reproduce by some counting method the area entropy relation. You have to also show that if that is your definition of entropy, if you add the entropy of the external stuff, then that total entropy will increase. And I'll just come back to this point. I'm glad that Paul is going to talk about it more tomorrow, that causal horizon entropy more generally should also be, a generalized second law for causal horizons should also be proved. Since black hole entropy holds the key to quantum gravity, the generalized second law can be a guide towards quantum gravity. So we can use the generalized second law to guide us in certain directions in quantum gravity. Sorkin has set out a proposal that the generalized second law arises from the non-decreasing nature of minus the relative entropy between any external state and a state that's constant under the autonomous evolution outside the horizon. And that's a very beautiful, elegant idea. Unfortunately, there's a lacuna, which Aaron identified. And the question is, how do we complete the proof? Is the Hartle-Hawking state thermal on these nice slices? Can we show that the non-increasing quantity that's guaranteed to exist by the theorem is proportional to the appropriate free energy? Although there are many approaches models which claim an area entropy relation for horizons, the generalized second law can point the way. It can distinguish between models. It can say this is a favorable model, this is an unfavorable model. Work by Wall shows this. The generalized second law can rule out non-singular black holes and bouncing black holes, bouncing universes, in fact. And here's a concrete question. Can we, in any of these cases where we have a non-singular black hole, can we exhibit a perpetual motion machine? Can we construct one from one of these non-singular black hole models? And Wall also provides evidence that the generalized second law supports the event horizon as the definition of a black hole over dynamical or trapping horizons. So if the generalized second law holds in full quantum gravity, it would be truly a beautiful unification. And it would mean that the discovery of Stephen's discovery that black holes radiate was the historic moment which opened the door to achieving that unity. And I'll just leave you with a list of references. Thank you.
A couple of points. One is that what you've said could be the jumping off point for the next great phase of investigation, which is to to look at black holes in systems which are far from equilibrium. And there's been a lot of recent advances, not in anything to do with black holes, but in non-equilibrium statistical mechanics and the second law. So something called Jarzynski's inequality. I may not pronounce that very well, but the work of Jeremy England is particularly noteworthy, I think. So I think there's been a really major advance in this field conceptually in the last 5 years or so. And then the other point I was going to make is you mentioned in passing about rotating black holes and there's no Hartle-Hawking. I can remember Roger Penrose saying a long time ago, if you put a rotating black hole in a box, then it eventually will reach equilibrium and there'll be some rotating pattern of radiation. There'll be a state anyway in which it can be in equilibrium. So I suppose that would be a sort of analog of the Hartle-Hawking state, whatever it is.
Yes.
Don't think anyone's worked it out. So just 2 comments.
Yes.
So I guess I'm asking for clarification. It looks to me as though you're saying Wall shows that if the generalized second law holds, then, and we have smooth Lorentzian metrics, then we must end up with black holes.
No. He's saying that if the generalized second law holds,
because he
then
rules out all the things that are...
You can't have smooth
No,
Lorentzian metrics. You have to have there has to be a singularity. In the same, that it has to be null geodesic incompleteness. In the same way that Penrose. I mean, the proof goes forward just as Penrose's original.
Right. So he's arguing that we must have singularity.
Yes, he's arguing we must have them. Yeah.
Which I would say is a black hole. But maybe...
Oh, I see.
Yeah.
Right.
So
if we assume the cosmic censorship holds, then yes. There must be what I would call black holes. But I just want, because people have been using black hole to mean non-singular things, I didn't want to assume that to say black hole means that there's a singularity. So, but I would agree with you.
So a corollary would be that if, say, if Stephen and Malcolm are correct and that we now understand that there's no information loss in black holes, and if we understand they can evaporate completely, then the generalized second law can't hold.
Well, one would have to say the generalized second law would have to mean something else. In some sense, this is almost a fine-grained generalized second law in the sense that the coarse graining that you have to do to get this result is the most objective coarse graining you can possibly imagine, which is just to trace out what is unobservable behind the horizon. So it's sort of objective in a certain sense that the coarse grainings that you usually have to do when you're proving a second law are not. But if there's no event horizon, and you therefore don't trace out over anything, then the second law kind of holds trivially in some sense because the state is just pure and it remains pure and the entropy is zero and it always is zero. So one would have, I think the onus is then on people who think that the evolution is always unitary to explain what it is that they mean by.
But the proof that you demonstrated the generalized second law required an horizon.
Yes. And I think in this work, say for example showing that the generalized second law doesn't hold, say, for the dynamical horizon, I think there he's just assuming that you do the same thing, that you trace over the states of the matter inside the, in this case, dynamical horizon. You choose the area of the dynamical horizon to be the entropy of the of the black hole in inverted commas, the non-singular thing, and you show that that quantity, the sum of those two things, can decrease. So that's, I mean, so you do what you would do if it were an event horizon, and you show that that quantity will decrease.
And so in that calculation, was the dynamical horizon taken to be space-like or time-like?
A dynamical horizon is, Malcolm, do you know?
Precisely.
I think it's space-like, actually. I think it's space-like, the dynamical horizon.
Yeah. Okay. Yeah. In your discussion, you didn't say anything about assuming an energy condition, but I think it must have been implicit in the proof of the generalized second law that you sketched, because you pretty much have to have some kind of some assumption about energy conditions. Although, I mean, you have a pretty clear counterexample. That is, if you could create a pure quantum state that had unlimited amounts of negative energy in it, then you just shine that negative energy onto the black hole and you pre-evaporate it. And you basically decrease the area without necessarily a corresponding increase in entropy someplace else. So could you say where's the energy condition? Where does it slip in?
We're assuming the first law.
Well, the proof of the second law, I think there must be an energy condition somewhere. I'm not sure where. It doesn't have to be a local energy condition. It could be an averaged energy condition.
Is it somehow implicit in the Howard-Hawking statement?
Well, it could be in this case, but I think more general proofs of the generalized second law have to say something about energy conditions. I'm pretty sure that Wall's proofs have some type of an averaged energy condition as one of the postulates.
I think that's not true. I think that the generalized second law in that case is an assumption rather than a conclusion.
Well, yeah,
So,
in that
so,
case, but
yeah.
in the cases where you try to prove the generalized second law, starting from other assumptions, I think one of the assumptions has to be something involved an energy condition or equivalent to avoid the counterexample that I just gave. Where
So what would be violated in that case? Yes, that's a good question. I don't know what...
Well, I think with the
you
Hartle-Hawking
think
state, there probably isn't any problem because the matter here is just thermal radiation,
Yes.
which necessarily automatically satisfies energy conditions. But if you want, I mean, so this was kind of getting to the next point I wanted to make, that in a sense, when you're using the generalized second law, for example, to restrict wormholes, I think another way of saying what's going on is that both the generalized second law and restrictions on your ability to build wormholes depend on quantum field theory having restrictions in them, what some of us call the quantum inequalities. That is, that they're at least in flat space, you can prove fairly rigorously restrictions on the sample time-integrated energy density along geodesic observers' paths, and those are fulfilled by quantum field theory,
Right.
and of course they carry some of the same content that the generalized second law has. They're what prevent you from giving the blatant counterexample that I gave, but they also show why you can't, for example, build traversable wormholes, because you would necessarily, at least macroscopic traversable wormholes, but you would violate these inequalities.
I agree with that. I mean, I think one could ask which of the two conditions is stronger. I mean, perhaps
Yeah. So
perhaps an assumption that the generalized second law
yeah. So
holds perhaps implies these
Yeah, I
these
think
average,
you
these
can
average
work-
energy conditions.
Yeah,
Which then,
that's right. You can work it both ways.
Yeah,
but
I think that's absolutely right.
There's some equivalence. But
I
if you
think-
want to try to prove the generalized second law, starting from, say, microphysics, then I think you have to go through some restrictions on energy. And that kind of brings me to the next point, that is the quantum inequalities have been proven fairly rigorously, at least in flat space and certain other space-times for free fields. But they haven't really been proven for interacting fields. Yep. So I think there's still a question then. I mean, we have reason to think that we expect them to hold. But I think that's still, I think it's an open question to what extent the generalized second law on the one hand or the quantum inequalities on the other hand will hold for general interacting field theories. I don't think that's really been explored well enough yet.
Yeah. I would like to make a comment. Oh, sorry, if you want to answer. I would like to make a comment in the same direction of what Larry just said, that usually when you work in trying to do singularity resolution in quantum gravity, at least in loop quantum gravity, you start from the full theory in which you have a fundamental space-time discreteness. And then you work out your effective equations and you find a new term. And this new term is a modification of the gravitational part of the Einstein equation. But then once you went semi-classical, well, you can decide to move this new term on the matter part and say, oh, okay, everything goes as if there was a violation of the energy condition. So in your fundamental theory, if you do things properly, you have never violated the energy condition. It's just that when you want to describe things out of the regime in which you originally worked, then you can think as everything was, as things were violating the energy condition. And I have the impression that here there is some confusion about the domain of application of the theorems that we are talking about, because so there is this the theory state an equality between the energy condition and the generalized second law, but it seems to me that this is something valid in the domain in which quantum field theory in curved space-time is valid. But if you want to describe bouncing cosmologies, bouncing black holes, then in that specific region, you should use a full quantum gravity theory.
Okay. Probably none of these questions can be fully resolved until we have our full theory of quantum gravity. Even questions of exactly what quantum field theory in curved space-time means can't really be resolved until we have a full theory of quantum gravity. But if one pins one's hope on or is guided by or inspired by the unity of physics, then hoping to get out a generalized second law, having it be true in the full theory. I mean, I don't mean that it means anything in the deep quantum regime, because of course, as far as we know, entropy has to be associated. To even talk about entropy increase, we have to have some notion of entropy at one time, which for now we just have to associate to some hypersurface, and entropy at some other time, which for now we have to associate to some hypersurface. Those are semi-classical concepts. So what I mean by saying that the generalized second law holds in the full theory is that when we have the full theory, in a state in which the semi-classical approximation holds, then using the full theory in that situation will give us the generalized second law. So I don't mean that it has any meaning or you can make sense of entropy increase, well, necessarily. Maybe it does, in fact, but it may be that we can't even make sense of it in the deep quantum regime where there's no space-time at all to talk about. But I suppose that what I'm advocating is that the generalized second law can be used as a guide. So, for example, if you have a non-singular black hole model, then can you try and produce what I would call a gross violation of the second law? In other words, a perpetual motion machine. I mean, that would be I would consider that to be a bad thing. I mean, you could just say the generalized second law just doesn't hold. Okay, that's, you might be able to live with that, but I think being able to produce a system which is in perpetual motion, I think that's the bad thing. So, for example, Ted Jacobson and Aaron I've forgotten his name now. Another collaborator argued that if you have in Einstein ether theories where you have more than one metric, so in bimetric theories, for example, where black holes have two horizons defined by the different causal structures of these two different metrics, then in such theories, you can produce perpetual motion machines from such black holes. And that seems to me to be quite a black mark against such theories, such that you wouldn't want to. I personally would think that was a reason that would be something which disfavored such models.
I'd like to come back to the dynamical horizons again. I think it may bear on some of the comments we've just had. So I think you're right. If we're dealing with classical general relativity and matter does obey the energy conditions so that positive energy can fall into the horizon but not negative energy, then the dynamical horizon will be space-like. But as you pointed out earlier, quantum fields violate the energy conditions, and so we can have near a thing that's forming a black hole, we can have negative energy density. And if some of that falls into the black hole, the apparent horizon is no longer space-like and becomes time-like. So my question would be, it'd be much more interesting to see if in the case of time-like dynamical horizons, they can show that, in other words, if we allow the black hole to collapse instead of just expand, to evaporate instead of just grow interminably, is the generalized second law recovered? So you're saying if we allow it to expand indefinitely, then it doesn't hold. But if we allow it to evaporate, is it possible that it does hold?
My understanding is that that's ruled out by Aaron's theorem.
But how? He hasn't. It depends whether he's using dynamical horizons, which is space-like or time-like.
Okay, could I comment on that? I think this is a point where it's very important that you're, as Fay pointed out, you're talking about the full event horizon, not the apparent horizon. That's very crucial in this. And you can give a simple example. That is, quantum field theory does allow you to have local negative energy. But at least if we're dealing with quantum field theory in flat space-time, the magnitude and duration of the negative energy fluxes are highly limited. And what's more, they have to be followed within a fairly short time by compensating positive energy. So if you create a negative energy flux, you can send it into the black hole, but then you must send in a larger amount of positive energy within a fairly short time. In fact, the longer you wait, the more positive energy there have to be. That's what Tom Roman and I call the quantum interest conjecture. It's actually proven, so it's more of a principle. Now, and here you can see where how that saves the generalized second law, because the true event horizon does not respond locally to the instantaneous energy as a global construct. So in this teleological sense, the true horizon knows the future. It depends upon the future positive energy that's going to come in, because it's the future history of the rays that in the end are just barely trapped. And that future history is dependent upon the positive energy that's going to come in after the negative energy. So in fact, then, as long as you use the full horizon for your generalized second law, you're okay. But you would run into a trouble if you tried to use the apparent horizon.
But if black hole evaporation occurs so that there is no event horizon,
Yeah.
Well,
then the only theorem
why
we
do you
can
say
use...
that, Bernard?
But
I
you-
mean, here's a picture of black hole evaporation.
You have the thermal radiation too, though.
Well, that's the black hole evaporation with a remnant.
No, there's no remnant. It just disappears then.
Oh,
This is completely regular.
yeah, it's okay.
There's no remnant. So nobody knows whether that's right, but do we know it's not right? Then there's an event horizon, right? Because the boundary of the
Yes,
of the
okay.
causal past of Scry plus is this.
Okay, so if we have singularities,
Yeah.
then we can use this theorem.
Yes.
If we have no singularities, we can't have an event horizon. If the evaporation leads to a completely regular space-time, so we don't have
I suppose
singularities.
the general idea is that if there's no singularity, and then I suppose the general idea is that the overall idea is that there's no way to define a generalized second law. In the sense that, so you would have to say that nature is,
Well, in
nature is
the
malicious, right? I mean, this, you would have to say, yeah, that was, you thought that was so at some, some stage of science, but actually it's not. That would be malicious. Nature is subtle but not malicious, I would say. So without a singularity, without an event horizon, I think the idea is that there's no generalized second law.
So in the kinds of geometries that Francesca was looking at, those apparent horizons exist for the duration of the evaporation, which can be many times the life of the universe. But technically there is there's no event horizon. There's no singularity, there's no event horizon.
Then I think the claim is that any attempt to
There is
define what you mean by a generalized second law, to associate entropy to the object, the object which has this horizon. Any attempt to do that and have a generalized entropy that always increases fails. That's the. So you could just say, yeah, so what?
Well, that's what I'm trying to understand. So in those geometries that she described, the apparent horizon, there are parts of it which are time-like. And they're, in particular, they're time-like during the evaporation. And I'd like to understand if the theorem that you quoted from Aaron Wall, holds for time-like dynamical horizons or only for space-like dynamical horizons.
I don't know. We can look and see.
So I consider it important because if it holds for time-like dynamical horizons, then the entropy that we can associate with hidden behind this dynamical horizon could allow the generalized second law to be restored. So first of all, defined, and then to hold.
We can see.
Just as long as you have the large positive entropy and the thermal radiation going outward, then you may not need it may be okay for the black hole entropy to decrease. That's the usual picture of the Hawking evaporation.
Right.
But if the total dynamics is unitary, then that eventually the radiation will all be in a pure state. So
Yeah. Well, then everything's zero.
then everything goes back to zero. So that's a sort of trivial. I mean, it's violated.
Well, we could imagine the quantum field states that are causing the collapse not to be pure states, to be mixed states. So we could allow that there is entropy to begin with. So it wouldn't necessarily go back to zero.
So it will go back to whatever it was in the
Right.
beginning. Yeah. So it would decrease to whatever
would
it was in
change.
the beginning.
I think someone else had a question. Did they?
Any more questions or comments?